chemical physics. Today I'm going to run through a few undergraduate, high school level physics questions. So here's the first one. It just says dashed lines in the diagram. I'm just going to draw out the diagram. And so we've got a number of equal potential surfaces represented by these dashed lines and given their values. And that's 1 volt, and that is 0 volts. And I got a minus 1 volt and a minus 2 volts, and I believe also a minus 3 volts. And then there's a couple points, B and A. There's a couple other points, but they're not important for us. And the question just asks, how much work is done in moving a 1 coulomb charge from A to B? So our work is our force times our distance, but we're not given forces or distance, we're just given our potentials. But the way I like to remember all of our relations, especially on electrostatics, is that force is related to potential by a multiplication of minus dx. Potential energy, I should say. Potential is related to potential energy by a multiplication of charge, and it's not super important for this one, but it completes the square. Multiplication of charge takes you from electric field, and electric field goes to potential with multiplication of dx, or minus dx. So in this case, we've got potentials, and we've actually got a delta potential. So that means that going from a delta V to a delta U, we just multiply by Q. So delta U is Q delta V. Okay, and so that's the right-hand portion of this. So now we've got our change in potential energy and going from A to B, and on the same time, our change in potential energy is, using this arm of the square, is just minus the force dx, or if we just want to, well, yeah, I'll keep it as dx, like that. And so comparing that to our expression above, then our change in energy is just our work, or the negative of our work, actually. And so that means the negative of our work, relating these two expressions, oops, and I didn't realize there was stuff in here. So that means the negative of our work is just Q delta V. And so our work is Q delta V. Now looking back at the question again, point A and point B are both at 1 volt. So V for both is 1 volt. So that means Q delta V is just 1 coulomb times 1 volt minus 1 volt. Now that's just 1 coulomb times 0, which is 0. So our work, which many of you might have heard, but we've expressly shown it. So our work in moving along an equipotential surface is 0. Okay, so let's look at the solution. So the work done in moving a charge from point A to B is related to the potential difference. We know that the work is negative, hence the equation for work is this. Given those values, we get 0. So the solution is correct. And looks good. And I'm just going to grab a new one. Alright. And, okay, so the second question asks, what is the acceleration due to gravity on the moon's surface? So our gravitational equation is just Gm1 m2 over r12. So in this case, well, for all cases, I guess, the gravitational equation, the gravitational constant G is 6.674 times 10 to the minus 11 newtons, and that should be squared, sorry, meters squared per kilogram squared. Now in this example, we're going to use M1 as the mass of the moon, which would be 7.346 times 10 to the 22 kilograms. And R12 would then be the distance from the center to the surface of the moon, or the radius of the moon. So the radius of the moon is just 1.738 times 10 to the 6 meters. And we want the gravity on the moon's surface, so we actually don't need the M2. And to illustrate this, well, our force is just Gm1 m2 over r12, and that force is going to be m2a, right? So F equals ma, where m2 is the mass of whatever the object is we're considering, and that's the gravitational force. So you see here that m2 cancels in both cases, or both sides of the equation. So then that means that A is our acceleration, which in this case is our gravitational acceleration. So A is just equal to Gm1 over, and I keep dropping that squared, over r12 squared. Okay, now filling in our values. Our gravitational acceleration is 6.674 times 10 to the minus 11 newtons meters squared per kilogram squared. Mass of the moon and 1.738 times 10 to the 6 meters, meters squared. Okay, so just doing a quick unit check here. So we've got meters, they'll be squared down here, so they're going to cancel this. This kilogram will cancel one of those. And then remember that a newton is a kilogram meter per second squared. So that means this kilogram will cancel the rest of the kilograms and leave us with meters per second squared, which is a unit for acceleration. So that's great. That means we've likely not made any mistakes because the units work out, and that is unlikely to happen if we made a mistake. Or at least is one of what I would recommend is one of the first checks you should make if you think that you made an error. Okay, so running this through our calculator, we get our acceleration is 1.623 meters per second squared. And so the gravitational acceleration on the planet of the moon, or the surface of the moon, is 1.623 meters per second squared. Checking the solution. So we just use this expression. So they're just starting from just an equation for it, but I often just opt to not remembering a bunch of equations, but just the primary equations, and then knowing how to get to each piece, but it's up to you. And so you fill in the numbers and you get your gravitational acceleration. So that looks good. And grab a new one. Okay. All right. And now this question, I'm going to just draw it out here. So we've got a positive charge, and a point. And it says that, now let's see if I can do this. Okay, it says that that's our, and the charge on this guy here is 3.0 nanocoulombs, and the charge on this guy here is 3.0 nanocoulombs. Okay, and so it asks what the magnitude and direction of the electric field at the position indicated, so that would be this guy, by the dot in the figure. So first off, we need electric field. So again, I'm just gonna, and also this is question 3. I'm just gonna go through this little square I've drawn before. And so force and electric field are related by charge. Potential energy is by a minus dx. Potential is charge, and potential and E field is by dx. I just mentioned it because I usually remember the force equation, which is the force from electric charges is 1 over 4 pi epsilon naught Q1 Q2 over R squared, R12. So the E field equation, and I should also say R12 R hat, just so that, because we're going to be dealing with more than one dimension, so it's going to be handy to keep our vector notation in hand. So going from force to electric field would be division by Q. So get rid of one of those Q's. So then E is 1 over 4 pi epsilon naught Q1 over R12 squared R12 hat. Okay, so that's our E field expression that we're going to use to solve this. The other thing we're going to need is to set up an axis system. So let's throw the origin right in the middle, and we're going to have X go this way, and so that'll be our X hat. And we're going to have y go up right this way, y hat. And so then now we need to define a couple of our R12 vectors. So going from this positive charge down to here, and I'm going to call that R1. And going from here up to here, and I'm going to call that R2. Okay, so R1 is, so looking at it from the positive charge, right? So that's minus R in the y hat, minus x in the x hat. So minus R x hat, minus R y hat. The magnitude of R1 is the square root of the sum of the squares, so r squared plus r squared, which is root 2r. And so r1 hat is r1 vector over, I'm just gonna erase that and fix it, r1 vector over the magnitude of R1 vector. I'm just going to scroll this up. Which equals minus R over root 2R x hat minus R over root 2R y hat. So the R's will cancel, giving us minus 1 over root 2 x hat minus 1 over root 2 y hat. Okay, so there's all of our stuff for our one vector. And now looking, we can see from that our R2 vector, which goes from this charge to here, is plus r in the y hat and minus r in the x hat. Minus r in the x hat and plus r in the y hat. Oops. No, you bad thing. Stop that. What did you just do to me? Oh, alright, you go there. Sounds good. Okay, so R2 vector is what did I say? Minus r in the x hat plus r in the y hat. Magnitude of R2 is just root r squared plus r squared, so just the x component squared plus the y component squared, which is root 2r. I'm just going to circle these to differentiate them, and also because I'm going to need them later. Okay, and so then the R2 hat vector is again minus r over root 2r x hat plus r over root 2r y hat. The r's are going to cancel, and so R2 hat is minus 1 over root 2 x hat plus 1 over root 2 y hat. Alright, so now it's going to be helpful to collect everything we need. So I'm just going to move up everything here. So we have that our electric field due to a charge is 1 over 4 pi epsilon naught times the charge over r 12 squared times r12 hat. So this is the distance between the charge and the point. and the unit vector between the charge and the point. So we've got two charges, 2 points. So our total electric field will just be the sum, but we can break it up into the different pieces. So we're going to have an E1, and that's going to be 1 over 4 pi epsilon naught. The charge is 3 nanocoulombs. The R vector is just the magnitude, which, if we look, right, both of our magnitudes, our R1 is just root 2R. So it'll be root 2R squared, and then multiplied by our R1 hat, which in this case is minus 1 over root 2 x hat minus 1 over root 2 y hat. Right, so that would be our R1 hat, which is this guy here. All right. So now, just multiplying this through, I'm not going to bother doing the calculation for 4 pi epsilon naught, since we're also not given the value of R. So I'm just going to leave things the way they are. And so this will be 3.0 nanocoulombs over, so root 2 squared is going to be 2, so this will be 8 pi epsilon naught R squared. So that's just this piece. And I'm going to keep the, or I might as well, I guess, pull the root 2 out just for simplicity here. So I'm just going to pull out the root 2. So throw the root 2 out front. And then this will just be minus 1 x hat minus 1 y hat, like that. And now we're going to play the same game with 2. So the electric field due to the second charge is 1 over 4 pi epsilon naught, 3.0 nanocoulombs, and that's because our second charge in the figure is also 3 nanocoulombs. And so, and also if we look, our R2 magnitude is root 2R, which is this guy here. And our unit vector is similar, but with a positive on the y. Okay? So this would be root 2R squared, and then minus 1 over root 2 x hat plus 1 over root 2 y hat. So again, I'm not going to bother calculating everything because we don't have the value of R anyway, so I'm just going to leave it as is but pull everything out. So root 2 squared is 2 times 4 is 8, and I'm going to pull the root 2 out here. So this would be 3.0 nanocoulombs over root 2, 8 pi epsilon naught R squared, and then minus 1 x hat plus 1 y hat. All right, so now our E total is just the sum of these two. Which is 3.0. I'll make a new line so I don't run out of space and don't have to squish too much. So it's going to be 3.0 nanocoulombs over root 2, 8 pi epsilon naught R squared, minus 1 x hat, minus 1 y hat, so that was 1. And then we're going to sum with 3.0 nanocoulombs over root 2, 8 pi epsilon naught r squared minus 1x hat plus 1y hat. Okay, so that's 2. We can pull out this prefactor because it's all the same. Leaving us with just our vector math. So minus 1x hat, minus 1y hat, minus 1x hat, plus 1y hat. And so the minus 1y hat and the plus 1y hat are going to cancel. And then the minus 1s are going to double up. And then this is going to give us our final answer, which is minus 2 times 3.0 nanocoulombs over root 2 8 pi epsilon naught r squared x hat. So we could do a couple things with the numbers, but I think since we already are going to leave r and epsilon naught, it doesn't really matter. So I'd say this is our final answer. But again, we could, we could make this into a 6, and we could work the numbers through. But in the end, we can use this to solve for our electric field, and we can see that it's in the negative x direction. So it's it asks what is the direction. So that's the magnitude. I guess I should finish the question. So the magnitude of the electric field is the square root of the x component squared plus the y component squared. There's only an x component, so it's the square root of minus 2 times 3 over root 2, 8 pi epsilon naught r squared. So the square root of something squared will of course give you the same thing back, but when you square it, it's gonna get rid of the negative sign. So that's really all that matters. So the magnitude of it is going to be 2 . Okay, so it's unsigned. The magnitude doesn't have the sign. So that's the magnitude of our electric field. And the direction is in minus x. So it's towards the left or in the minus x direction. Okay, so now looking through the solutions here. Okay, so k q over r squared. So k is the same as 1 over 4 pi epsilon naught, depending on whether you want to use which constant you want to use, but they're equal, so it doesn't matter. It chose to use 45-degree angles rather than the 1 over root 2. Again, that doesn't really matter. And they pulled all the numbers together, but I presume it must come out to be the same. And so the magnitude is a 1 over r squared, and the direction is to minus x, or towards the left. So barring any calculator errors, I would say the solution is correct. Okay. So a conducting loop is halfway into a magnetic field going into the page. What happens to the loop when the magnetic field strength suddenly increases? All right, so here we've got a conducting loop. Oops. And I'm just going to fix that slightly. And there's our conducting loop. All right. And we've got a magnetic field going into the page. I'm just going to kind of cover it with X's, showing that it's going into the page. So there's our magnetic field. Okay, so if we have a magnetic field going into the page and we suddenly increase the value of it, then we're going to generate an electromotive force in our conducting loop. Now the rule here is that the force direction, or what will happen basically, the end result of us changing our B value to some B plus delta B is going to be a current in the wire, and the current is going to be set up in the wire such that it opposes the change. So that's the key thing to remember. So it's going to generate a current in the wire. So to figure out the direction of the current, we're going to use our right-hand rule. And in this case, our right-hand rule is where, let's see if I can, well, I can draw this here. If we point our thumb in the direction of the current and curl our fingers around the wire, then the fingers that we curl will be the direction of the B field around the wire. So remember, a B field is circular, so it'll go around the wire. And if we look at this, right, so we're going to increase our B field downward, so into the page. And considering mostly the ones inside the loop, so those are going to be where inside the loop is where the B field from the loop is going to be concentrated. So that's where the largest opposition is going to happen. So that is what we're going to consider is inside the loop. Outside the loop, it's going to be sparse, and we're going to have, so there's no way we're going to get opposition inside and outside the loop because it's circular. But inside the loop is where the biggest difference is going to happen. So that means that if we increase the B field going into the page, what we need is a B field from the loop, which is out of the page. So we need the loop's B field, at least here, to be out of the page. Right? It's circular, so that means that out here it's going to be into the page, which is not going to oppose the change in the B field, but in here it's going to be much more concentrated, so that's what matters. That's where the net opposition is going to happen. So now if we play this game with this right-hand rule, right? If we curl our fingers around, right? So that would be a B field that looks like that and like that. Then we'll see that the current in all around it is in this direction. So that's the direction of our current. And I should mention that this is a positive flow of current. So this is considering the positive flow of charge. So actually negative current would go this way. So negative charges are actually flowing in the opposite direction, but that's okay. So this is the way our B field is set up. So that's our current. Now, what the question asks is, what happens to the loop when the magnetic field strength increases suddenly? So a few things happen. So first we get this current set up, but then a force on a moving charge, which is a current, right? So a current is charge moving. So the force on a moving charge perpendicular to a B field is given by this expression, where again we can apply our right-hand rule, where if we point our fingers in the direction of the velocity, and either curl our fingers or our palm will face in the direction of the B field, then our thumb points in the direction of the force. So in this case, our velocity, if we consider just, so it depends on which section of the wire we use. So here our velocity is downward, and our B field is still into the page. So now that means if we apply this right-hand rule, the force on this segment of the wire is to the right. If we apply it on the bottom segment of the wire, then we would find that the force is upward. And if we apply it on this segment of the wire, we would find that the force is downward. So that means that there's a net force out of the B field. So there's a net force outward. And so by increasing the B field suddenly, we generate a current in the loop, which generates a force that pushes the wire segment out of the B field. All right, and so that's what happens. Okay, so Faraday's law. So if we look at the solution, Faraday's law states that the rate of change of magnetic flux is equal to the induced EMF. So we could have calculated that given some parameters, right? Because the rate of change of our flux, again, just considering this portion here, is just the change in our magnetic field times the area. And so Lenz's law states that the direction of the induced EMF will be such that it opposes the change. And so it will oppose, as we said, so that's why the current is in the direction it is. And so this doesn't really give the answer. It doesn't say the current, and it has an arrow, but it doesn't really, that's, I guess, supposed to be the force, but I'm going to say that the solution is incomplete. Will be a counterclockwise positive charge current generated, which subsequently results in a force which pushes the coil out of the magnetic field. And I would say it's correct, but it doesn't really answer the question. Answer the question. So I guess I'm going to say it's incorrect, although everything said is correct, but when you just say a bunch of correct things, it doesn't necessarily make it correct. Okay, so this question is asking what the magnitude and direction of the current in the 20 ohm resistor. So first I'm just going to sketch it out here. So so this one's a fairly simple Kirchhoff question. And so we've got a 9 volt here, a 6 volt here, a 10 ohm here, and a 20 ohm here. So this is the resistor it's asking about, so it wants the magnitude of the and direction of the current. So to solve this, so whenever you see multiple batteries, this is a good sign that it's a Kirchhoff Law question. And so we need to essentially make a loop. So we're going to go from A to B to C to D and then back to A again. And now whenever we pass over a resistor, we're going to generate an equation. And so it'll be 0 equals, and whenever we pass over an equation, so in this case 10 ohm, or whenever we pass over a resistor, in this case 10 ohms, we're going to go minus, this will be minus IR1, so that'll be the current through the resistor times the resistance. And also recalling that your current either will be maintained, like in this case where you have one loop, or if there's splits, the current will split based on the resistances in the split. In this case, we only have one loop, so the current will be the same around the entire thing. So we can just use IR1. And then the rule for going across batteries is if you go from positive to negative, then it's minus the voltage. And if you go negative to positive, then it'll be plus the voltage. So A to B, B to C, C to D gives us minus IR2. Or I guess I might as well put in the values since I'm putting the values for the voltages. So this will be 10 ohms. And this will be 20 ohms. And then going from D to A, since we're going from negative to positive, is plus 9 volts. And I should have said that when you go over a resistor, it's minus IR as long as it's in the direction that we're going. So in this case, we're going this way, this way, this way. As long as the current is flowing this way, I should say. So in this case, we're assuming the current's going clockwise. And so each of these resistances get negatives. If the current comes out to be negative, that means we assumed wrong and the current's actually the other direction. Okay, so now we have our equation and we can solve it. So we've got 0 is equal to minus 10I. And I'm just going to collect things, so I've got a 20 over here, so that actually should have been a minus 30. And then we've got a minus 6 plus a 9, so plus 3 volts. That's still an ohm. And so our current is minus 3 volts over minus 30 ohms. Negatives cancel, and that's 1 over 10 amps. Okay, so the current comes out to be positive, meaning our initial assumption that the current was clockwise was correct. And so, and that's our value. So the current through the 20 ohm resistor is 1 over 10 amps, and it's going to the left, or it's going in a clockwise direction. Okay, so looking to the solution here, applying Kirchhoff's rule, we get this equation, assuming a clockwise flow. We could solve for I, which gives us 0.1 or 1 over 10. And since it's positive, our clockwise assumption is correct. And so that's what we get. And so the solution is correct. A new sheet. Okay, so here we have a refraction question. So I'll just draw it up first. So we've got, yeah, that's a bad drawing from the get-go. So let's start over again. Okay. So we've got a prism, which we're just going to pretend that all these are straight lines. And it's a 30, 60, so that's 30 degrees, that's 60 degrees, and that's 90. Okay, so we have a laser coming in from the left, which then would go straight if there was no difference in refractive index, but it instead bends by 19.6 degrees. And it wants to know what is the prism's index of refraction. So we're assuming here that this is vacuum, which means that n is 1. So the index of refraction in vacuum is 1. Okay, so to do this now, this is really a Snell's law question. So n1 sine theta 1 is n2 sine theta 2. And first we need to identify what theta 1 and theta 2 is. So in this case, we need to draw a perpendicular to the surface where the refraction occurs, and then that will be theta 1, and that will be theta 2. Okay? So in this case, this is a similar triangle to the one that's set up. So theta 1 is just equal to 30 degrees. And so that means that although theta 2 is not 30 degrees, it does mean that that angle in there is 30 degrees. So that means that theta 2 is 30 plus 19.6, which is 49.6 degrees. And so taking n1 as 1, this means that we have 1 times sine 30 degrees is equal to n2 times the sine of 49.6 degrees, or n2 is equal to sine 30 over sine 49.6 degrees. What did I do there? Oh, oops. I know what I did wrong. Oops, so that was my mistake. So n1 isn't 1, n2 is 1. So n2 is where we're going into vacuum, so n2 is 1, so my mistake. So n2 is 1, n1 is what we're solving for. n1, n2 is 1. Oops. So then n1 is the sine of 49.6 degrees over the sine of 30 degrees, which when we run this through our calculator, and 1 is 1.523. So the index of refraction of our prism is 1.523. Checking the solution here. Okay, so they've used mu as index, which is fine. You can use whatever you want to call it. Solving for our angles. So that's just the summed angle there, 49.6. And they called sine 1/2 sine of 30 a half, which is fine. That is what that's equal. And so this is split out a little bit, but still we get 1.523. So it's exactly the same. So the solution is correct. All right. And what do I got here? Okay. So this one is at my 7th question. Okay, so we have a focal length. What is the focal length of a makeup mirror that produces a magnification of 1.5 when a person's face is 12 centimeters away? Okay, so just as a reminder of how mirrors work. So if we'll have the focal length of the mirror, which goes through the center, which is still what I'm going to pretend that is. And that was probably a mistake, but whatever. All right, so there's my mirror. There's my focal length. And if I have some object here that's in front of the focal length, again, that was a mistake because that's going to be impossible for me to draw. So if you have some object there in front of the focal length, then the rays are going to the rays are going to do something like this, and basically wherever this propagates to in the backside is our magnified image, where that is the x of our object, that is the x of our image, that is the height of our image, and that is the height of our object. And 1 over the focal length is related to our distances by 1 over the x of our object plus 1 over x of our image. Our magnification is the height of our image over the height of our object, but it's also equal to minus the x of the image over the x of the object. And remember that an x that's behind the mirror, which is a virtual image, will be negative. So that means that we're given that magnification is 1.50 and that the x for our object is 12.0 centimeters. So that means that solving this equation, specifically this one, for magnification, it means that the x for our image is mxo with a negative sign, which is 1.50 times 12.0 centimeters, which comes out to be minus, I forgot the negative sign, minus 18 centimeters. So the assumption that we had a virtual image is correct. And then we can use this value. We can use this value in our focal length expression. So 1 over f is 1 over x for our objects, so 12.0 centimeters, plus 1 over minus 18 centimeters, which, giving them the same denominator, is 3 over 36 centimeters. I guess I can drop the centimeters here, so it'd be centimeters the whole thing, or actually inverse centimeters. Yeah, I should have done that. All right, I'll leave the centimeters on the bottom. Minus 2 over 36 centimeters. So 3 minus 2 is 1, so that's pretty easy. And so that's equal to 1 over 36 centimeters, or as that's 1 over f, our focal length is 36.0 centimeters. And also validated our assumption that the object was in front of the focal length. And so that's, yeah, so that's just our focal length. All right, so looking through the solution, the magnification can be related to the distance between the mirror and the object, and the mirror and the image, like this. Substituting our values, we get minus 18, which is what we had. And from the mirror equation, we can get our focal length, which comes out to be this. 30, and yeah, so our focal length we get is 36 centimeters. So that looks good. And I'm going to say that. And I think I'm going to have to say this for another time. And I'm going to say thank you all for listening and watching. I hope you enjoyed these questions, and if you did, please subscribe, and you can leave questions for OneClass in the links provided below the video. This has been Jeff Krause for OneClass, and I